Thank you. So my name is Lars-Johan Liman. I work as introduced for a small company in Stockholm called Netnod. And I've been working with the DNS for way too long. Someone asked me in my early days, just thinking out loud, I wonder if you can make a career out of just working with the DNS. I can tell you, you can. What's Netnod? Netnod is a small company. It's actually a spin-off from the Royal Institute of Technology in Stockholm, the technical university. And we've been providing authoritative DNS, meaning the provider side of the domain name system since 1998, essentially. In doing so, we provide service to a good number of enterprises, organizations, companies, and private people through our systems. We don't interact with them directly because we have partners that have the customer interaction. We also serve about 80 top-level domains. .no for Norway is one of them, and .se for Sweden as well, and another 70-odd ones. That's another major part of our business, but we also serve, as David mentioned, we serve the root, the highest level in the DNS tree, which will direct you to the various servers for the national countries, Norway, Sweden, Denmark, Finland, whatnot, but also for the other top-level domains, the generic ones, the com, net, org, museum, bank, whatever. And on top of that is the root service and the root zone that we provision from these, so we provide access to from these servers. We have one of the biggest DNS anycast systems in the world. We have around 85 locations on the globe where we provide this service, and in total it's more than 400 servers providing DNS service. So we respond to several billion queries per day. We have two other business legs as well. Internet exchange points in Sweden mostly. We have exchange points for internet traffic. We actually do cooperate with Nix here in Norway to provide service in Oslo. And we also have our most recent business leg, which is to provide very precise time and frequency services. So you can, by connecting to our atomic clocks, you can have down to a microsecond precision in timing if you want to. We also do a lot of work for global coordination of internet stuff, and we're involved in some general good for the internet stuff, like coming here and presenting. So I will take you on a journey into how crypto is used in DNS, and it's actually these days it's mostly for doing authentication. But I will start actually in my early days. In 1984, I did my military service as a crypto assistant. Would you believe it? We were taught to master 12 different ways of doing cryptography and encryption. I was never into the actual mathematics, but to handle the machines to do this. And we were taught to be able to handle all kinds of messages, whether carried by couriers or telephone calls or radio or telegraphy or teletypewriter. Much of it was teletypewriters, fax, email, early versions of that and whatnot. And in spoken form, in written form, in typed form, punch tapes, whatnot. If it landed, it was encrypted, we were supposed to handle it. And we did so to a reasonable level. But they all have keys, and that's what's going to be the focus of my talk here. Because the crypto keys have to be replaced on a regular basis. The more you expose a key by using it, the more data will be encrypted by that key, and the more data your opponent has access to, the easier it will be for them to break your system. So you have to replace the keys on a regular basis, and that means that you have to have a system to distribute these keys. How do you do that? In old days, well, you could stack them up beforehand and take a bunch with you when you went on a run somewhere. If you were a submarine, you had to do that, or you could distribute it using a courier, because back in the day these were actual things that you had access to. And this system of key distribution is actually a sore point or a point of vulnerability for most crypto systems. If you can't distribute your keys properly, you can eventually no longer encrypt things, and that means that your system stops. So this is actually a picture of the very first crypto machine I laid my eyes on. This is a crypto machine 301s, the Swedish version of it. You can see, if you look really carefully, you can see the 3 crowns down here. That tells you this was government property. This one is placed next to, not connected to, it's next to a shortwave radio of World War II vintage. This is actually built more recently, but according to old specifications. And on the right, you see the inner keys, which have to be replaced on a regular basis, and in this case, daily. So these little punched paper cards needed to be replaced every day. I can tell you stories over beer about how not to do that. Or slightly more recent machinery would actually use standard IBM punch cards, not as you would use them in a computer, but it was actually the same piece of equipment. I didn't realize that until much later, that I had held in my hand these IBM cards during my military service. So how is it used in the DNS? Well, DNSSEC, secure DNS, is used for confidentiality. Sorry, not used for confidentiality. We are not hiding the content. We just want to make sure that the correct content is reaching the user, and that the user is able to validate, verify that the author is the person or entity who claims to be the author, and that it hasn't been modified in transit, so that you actually get what the other side sent towards you. There is a fourth thing you can use signatures for, but that's not used in DNSSEC, and that's non-repudiation, where you make it possible to ensure that the sending party cannot take back what they said. If someone promises something in a message, you can prove that they actually did say that at that point in time. So this is my caveat. We are not going to do the full training course on DNSSEC. That's a 3-day event, including training with computers. DNSSEC is full of infested with serious and nasty dragons. So this will be a quick overview where we'll talk about some principles. So these are not the actual details of how it works, but these are, fragments and pieces of how things fit together. So signatures, what are they? That took me a while to figure out. What they are actually encrypted checksums. A checksum is you can calculate a checksum by using a fixed and well-known algorithm and a piece of data. And when you do the calculation, you end up with a number that can be longer or shorter depending on your algorithm. And if you have the same data, the algorithm will always give the same output. And now the theory is that if you change anything, even the smallest bit in the input data, the checksum will come out different. There is always a risk for collisions, that 2 different pieces of data actually give the same checksum, but with modern algorithms, that's supposed to be extremely rare. So you should be able to trust it, and not something you can predict. You cannot construct a new set of data that generates the same checksum. So what you do is that you then encrypt the checksum, and that generates the signature. And in this, you use asymmetric encryption that was spoken about earlier. So where sorry, you don't have to do that. That's the common way of doing it. But you send the signature and you send the data. You don't have to send it in the same way. You just have to make sure that the recipient is able to understand that this signature belongs to this data. So if one comes in paper and one on a punch tape, just make sure that you can understand that they belong to each other. And then the recipient calculates same algorithm checksum over the received data, and then it decrypts the checksum that you have sent with the data. And if they match, you have the same data as the author sent. And you can also be sure that it was actually the author who sent the data, or at least created the checksum. Because if it wasn't, then the decryption wouldn't have worked with the crypto key. So this is the process in an old picture I tried to draw many years ago. That's still kind of valid. Here I have as examples old algorithms, the Samir Adelman algorithm. This is a secure hash algorithm, and this is the RSA encryption algorithm. So you first calculate the hash, you get the checksum, you encrypt that using private key, you get the signature, and you send that with your information. Okay, now we step into DNS land. In DNSSEC, everything is encrypted. In DNS, we have DNS records, which pertain to different types of information. We have always a domain name. The technical term is a resource record name. And to that, we connect some type of information, here an address, meaning an IPv4 address. And then we have the actual data that we want to store or convey in the DNS system. And in DNSSEC, we sign everything in our zone. The zone is the administrative delimited part of the DNS tree in the world that we administer. So my zone, I can sign my zone without bothering about anyone else in other parts of the world, except my parent, the one from which I have received my delegation. For Netnod.se, that would be the SC, the parent would be SC of Sweden. So we add a signature record to this one. This is the signature, and you will note that this is, this is a lot bigger than the data record itself. The data record is only a few bytes, 10-ish, where the signature is on the order of, well, many dozens, maybe 100 bytes. So the amount of DNS data that we get to deal with grows dramatically when we go with DNSSEC. This is a resource record signature over the address record. So you can see that they are tied together. They have the same name on the left-hand side, meaning these two belong together. And this is the signature over the address record. And then we have the actual signature down here, which is a text representation of the encrypted checksum. Okay. Now, how does the recipient get the key that it needs to validate this? In order to validate properly, it needs to decrypt the data blob at the bottom using a crypto key. So how does that happen? Well, to begin with, we use asymmetric encryption, where we have two keys in a pair and they go together. So if you encrypt something with one key, you decrypt it with the other key. And you can actually go the other way around. If you decrypt the second key, you can, if you encrypt with the second key, you can decrypt with the first key. But here we use it only in one direction. And what we do is we create a signature by calculating the checksum and using the secret key, the first key. And that's a key that I hold on to and I don't share it with anyone. And then I publish the public key widely so that anyone who wants to can get access to it. That means that anyone can use the key to decrypt something that I have encrypted with my key. And anyone can then validate anything that I have encrypted with my private key. So how do I publish the key? Well, on the internet, everything, the answer to that question is always use the DNS. That's the the kitchen sink that's used for everything. So we have to tell the user which key to use in order to decrypt the signature properly. And we do that in the same record. This is the same one as before, but I now point out that this is actually the name of a key. You have to look up this name in the DNS, and you can have multiple keys with the same names. You have to identify the key using something called a key ID, which is again actually just a quick checksum of the key. So there is a corresponding DNS key record in the DNS, which is essentially just a big random number, again, represented in text form. But it has a few flags in the record just to identify the type of algorithm this key is supposed to be used for, and a few other things. Okay, are we done now? We can sign, we have published the keys, anyone can validate. Well, we have to make sure that the key that I publish in my DNS server reaches you unaffected, and as you know, that's a whole key that hasn't been modified. So we have to make sure that the key wasn't altered in transitioning the internet. Well, we use the same method, of course. We add a signature to the key. All right, who gets to sign the key? Well, I do. Okay, fair enough. But do you trust me then? Then anyone could use my name to sign the key, or in Netnod's name. So why should you trust me? So this again turns into a problem. So keys in DNSSEC are built into a trust chain. And the DNS is hierarchical. We have a top level at the root. We have the top level domains, NO, SE, COM.net, org. And then we have various names and organizations underneath. You would have kth.se, netnod.se, volvo.se, and you would have names in Norway, the University of Oslo, and what else in Norway, and COM.net, and so on. And we create a chain where the parent signs the keys of the child. So I promise you that this is my key, but also my parent promises that this is my key. And if you trust my parent, the Swedish top-level domain, you can say, okay, they promise that this is Netnod's key, and then I can choose. It's a choice. I can choose to trust that key as well. Then we have created the first step in the chain. And then you have, on top of that, you have the root that will sign the .se key. It will sign the key for the Swedish top-level domain, and corresponding for the Norwegian one, and for the COM.net and org. So we create this trust chain, but we have to have a starting point. We must trust something intrinsically. We must trust something from the start. And the DNSSEC system is built such that we decide to trust the key for the root. So the root key is your trust anchor. That's where it all starts. And by using that key, you can validate the key for .se, you can validate the key for .no. And with the SE key, you can validate the key for netnod.se and the key for the University of Oslo. And so further down, step by step. That key is available here. This is the true actual place to go and to fetch that key. And it's also supposed to be so well known that it's, it's impossible, within quotes, to fake it. If I were to ask you, what telephone number would you call to if you have to alert the fire service? And again, it's your mother. Okay, 113 it is. So if I was here to say that, no, it's 258 today. If I were to say it's 258 today, would you believe me? No, you wouldn't. I hope you wouldn't. So that's a well-known telephone number, and the key would be, so to speak, equally well-known, that if someone comes and tells you this is the root key this day, you would say, no, I picked my key from here. That's the true one. So it's supposed to be well-known and therefore very hard to fake. So in the DNS name hierarchy, we have the root, usually denoted by just a dot, and it has a well-known key, and that key will then sign the keys of the next level in the tree, and that will sign further down the tree. So, are we done now? Do we have all the bits and pieces? We have a root key. We can access the keys for the top-level domains, and using those keys, we can access the keys of the lower second level domains, Netnode and DNSnode.net in this example, we can actually validate all the things. And with those keys, we can validate the signatures for the address records and whatnot. So we are actually done, aren't we? Well, sorry, not quite. How does the parent know which key to sign? How does the parent know that I'm responsible for the key for Netnode? And how does it validate the key when it puts the signature on it? That has to happen with out-of-band communications. We can't use the DNS to create that trust. We have to use some other method. Typically, this will be a web system where you log into something, or you create a business association, you pay for your domain, something you do over the web, or talking to your registrar for the domain names who have an access to the registry using often EPP, the extensible provisioning protocol that they use to inject stuff into the top-level domain database. We don't use the DNS for this. And that has to happen. But if we do that, the process for doing that, child generates a key, publishes it in the DNS. We then upload the key using this out-of-band mechanism to the parent. And again, this goes for every pair of levels. This is how it works when .se generates a key and submits it to the root, or when the KTH creates a key to submit it to .se and so on. Once it's uploaded and validated using this separate method, the parent can sign it and publish it. So this is used this is done using a record type called DS, delegation signer. And this record is, of course, in turn signed by someone. And note here, this is actually something that's slightly different from the last picture that looked like this. In this case, the netnode.se record is signed by the top-level domain key. In the last picture I showed, we had the netnode.se name signed by Netnode. Now it's signed by someone above in the system. So what happens here is that the Swedish top-level domain signs delegation signer information. This points out which key we want to use at Netnode. So the Swedish top-level domain promises that this key identity with this name is something that we guarantee and you should trust, that this key is used for this domain name and everything underneath until further delegations happen. And we, as the top-level domain, we guarantee this with our signature. So when you traverse the DNS tree, you will get these records. You can validate where the Swedish top-level domain says, for netnode.se, use the key with the netnode.se name and this key identity. And the checksum of the key, by the way, should be this number here. This is a checksum of the actual key that Netnode has submitted to the parent. Okay. So now we are done, aren't we? We actually have a method of submitting the key to the parent and have it all signed. But nah, we need to rotate these keys. The system is kind of done, but we can't have a fixed system that's cast in stone. We have to rotate the keys. So we have to repeat this procedure of generating a new key, publishing it, going to the parent, have it signed, and they publish the signature that we saw on the last page. But we're humans. This is boring. We don't want to do that. And to be quite honest, we're not very good at it. Humans don't do repetitive tasks very well. Computers are perfect for that. Humans are not. That's one of the reasons that we have computers. So we want to automate this. And preferably, we also want to stay within the DNS system. We don't want to create chains of dependencies where we depend on systems outside the DNS to rotate keys that are all inside the DNS. We don't want to use HTTPS with login procedures and whatnot. We have everything inside the DNS. Let's try to stay there. So CDS records were invented. That's actually a standard thing. Every problem in the DNS is solved by inventing a new record type. There's more truth to that than you would believe. So CDS records were introduced. These are child delegation signers. If I back up one slide here, or two slides, we have the DS record. This is stored with the parent. The parent holds on to this record. So the DS record for Netnod actually sits in the .sc zone together with the signature of that record. The same thing goes for NS records for the actual name server delegation. So there are a few records that are located in actually the wrong spot, but it has to be there in order to create the connections between the different levels in the tree. So the CDS record, on the other hand, is actually stored at the child level, and it's child delegation signer, and that's actually the child saying, this is what I want my DS record to be up there. But I cannot influence what's in that zone except by going to them and doing this out-of-band handshaking and whatnot. But oh boy, I really want them to publish this. So how, if I put that in my zone, in the Netnod zone, how does the parent notice that? Well, the first approach to that is by scanning. The Swedish top-level domain knows exactly which subdomains it has. It knows that Netnod is one. It knows that Liman.se is another one. And it can actually walk through them all and say, do you have a CDS record? Yes, you do. Okay, I will process that. Do you have one? No, you don't. Do you have one? Oh, that's the same one as last week. Do you have one? Oh, you don't. Okay, so by scanning all the subdomains, you can actually, pick out the ones that have these records in there, and then validate them. And if you want to, you can publish them as a new version of the DS record on the upper level. But scanning. Scanners are inefficient. They will look at a lot of domains that haven't changed. That's not really efficient. They're also slow. It will take a day or so to scan the Swedish top-level domain. It's more than 1 million subdomains that you have to look at. To each and every one, you have to ask DNS queries to see if there are any changes, and you have to store the information and compare it to what you already have from last week and whatnot. So it's slow, and it's actually a rather complex piece of software as well to just to handle all this. So no, that's where we are today. The Swedish top-level domain is actually scanned on a daily basis for these CDS records. I don't believe that Norway does it yet, but I'm very, very fussy on that. Switzerland does too, I believe. But what if the child could say, I just introduced the CDS record, please look it up now. So that would be very useful because we could avoid the entire scanning process. We could ditch the entire scanner software piece of monster thing that we don't want to support and feed. And it would all be so much quicker. Hey, I have a new CDS record. Oh, I'll check that immediately. Oh, it's done. Okay, published, done. So we could speed up things. So instead of having a polling system, as the computer scientists call it, we would go to an interrupt-driven one, which is much, much more efficient and much quicker. In the DNS, we have something called notify messages, which are sent typically from a primary server to a secondary server. You have multiple servers that hold your zone, and the primary can tell the secondary, it's time to do an update. I have new data, please copy. But what if you could use it for other purposes as well? So this is an idea where the child can send notifications to the parent, but it has to know where the parent is, because in the DNS, all pointers go downwards. You know where the root servers are because that's your starting point. But from that, there are only pointers downwards in the tree. So here we create something where the parent.se in my examples can publish information to say, if you want to send notify messages regarding CDS, child delegation signer, to me, please send them to port 5359 on this host. And we will receive your notification message and act on it appropriately. That's the trigger for the interrupt thing that causes the parent to turn the crank and say, look up the CDS record in the child. The notification message will of course contain the name of the child. It will look up the CDS record in the child. It will validate that it's okay, and it can then choose to publish that new record as a DS record on the top. And by adding a CDS record in the child for a new key, sending the notification, turn the crank in the parent, pick up and publish, you can actually rotate the key. So this is where discussions are today. This is not in operation yet. This is being proposed in a, you see, this is so it's called Internet Draft. So this is the precursor of an RFC document, the request for comments that govern the DNS protocols. This is a proposed mechanism that is about to be handled in the DNS operations working group in the Internet Engineering Task Force. The question is out for adoption. It's looking good. So this is where discussions are going on. And now we can automate the entire process. I just went through that. And by this, we are actually finally done. So this now all happens inside the DNS. Data is properly validated because everything is signed. The CDS record is, of course, signed by the child so that the parent can validate it. It happens in a timely fashion because it's interrupt driven now. We don't have the master scanner involved, and it's all automated. So this is actually all good. This works. But work continues. We weren't quite satisfied with this still. So my really old friend and former colleague Johan Stenstam from Internet Stiftelsen, the .se administrators, just presented at a symposium, the ICANN symposium, the DNS symposium in Vietnam. Was it last week? Yep. A new idea where to use something called dynamic updates instead, where the child can actually send the update in an authenticated way to the parent, and the parent doesn't even have to go through the process of picking up, validating and whatnot, because you have created beforehand. There's something you have to set up beforehand. You create a secure channel to the parent where you can send a signed message to the parent saying, please update my DS record immediately. So that's even quicker, and that's actually something that already works if you set it up the right way. The problem is this distribution of keys, because the traditional dynamic updates use symmetric keys, which are much more difficult to handle, but there are methods to do it with asymmetric keys that actually work in this case. So that's not being published yet. I know that Johan is about to write another one of these draft documents about that. It hasn't happened yet, and I don't think ICANN has even published the slides from that symposium yet. But that is in the works, I know. So stay tuned. That was what I was going to tell you about today. Any questions, remarks? Rotten tomatoes.
I can take one from here.
Sure.
So I was wondering about, so I saw the dynamic updates that seemed like a better idea, but general notification. My first reaction to that was that what a way to do an amplification attack is. The way you present it, it seemed like somebody could trigger the root servers to actually start thundering the child servers, or I might have misunderstood something.
Well, that's a matter of how you implement it in the parent, I'd say. because if you have rate limiting there, it will be hard. If you're only allowed to ask for one update every 2 weeks, it's unlikely that that will be an application factor. But it's something that you need to look into, absolutely.
Yeah, but is there any way of securing that an unauthorized request, like then you can block a request from by sending an unauthorized request, and then you're blocking it for 2 weeks or something like that? I'm not sure, but
yeah, reflection attacks are something that we deal with every day. So yes, every DNS transaction is vulnerable to that in some way. Yes, so it's something that you will have to build into the system. Obviously, you're quite right. Or protection against that is probably the right phrase.
A small question about the DNSSEC and your opinion on the poisoning of DNS by third parties that are trying to hijack connections. What's your view on that?
To me, DNSSEC helps a lot with assuring that the DNS information that you as a client get is the correct one. The cache poisoning problem is where someone else managed to put records that general users want to look up, but with the wrong information in the resolver, which is on the help server on the client side. So if they manage to trick that resolver into storing a record where the IP address for your bank is not the correct IP address, then the clients who ask for that information will be vulnerable. But with DNSSEC, the resolver is able to validate the content of the DNS information before giving it out to others. And DNSSEC is very, very efficient in helping there. That's, I would say, is the primary reason for going with DNSSEC, is to avoid that problem.
But it's not really a question of tricking. It's more like the government has, by law, required that you are going to poison DNS. If you are looking at popcorntime.com, I think you will get a different answer here in Norway. If you are looking for some services, the ISPs are required to poison DNS and return something else for gambling services and stuff like that.
I see your point. And so that's something where you as an end user still have the tools to validate. If DNSSEC is being used in all this, in the entire chain from the root down to this service, it could be that the resolver has a legal obligation to put something else in. But if you are really interested in this, you as an end client can actually do the full validation yourself, and then you will detect that. But it does require that you operate your equipment with the DNSSEC validation turned on, and there are very few and far between people that do that. But yes, it is possible. So the tool is there. Maybe it's slightly too complicated to actually use the tool, but we on the provisioning side cannot really do more than providing tools to validate things. We cannot run the validation for you. Please wait for microphone, please.
Yeah. So in those keys, I haven't noticed any description of the signing algorithm. So which algorithms are supported? Well, you mentioned RSA, but what about elliptic curves? What about post-quantum crypto?
I haven't really, dived into the post-quantum part of things yet, but the algorithms that are currently used for DNSSEC signing to some extent is the old system. People who want traditional stuff, they use RSA, and more recently, people have started to shift towards elliptic curve with the DSA. Because that's much more efficient. One thing that we worry about with the DNS is the size of the packets, because we want DNS to be small units of information that you can send quickly, because it's something that it's a precursor to almost every connection on the internet. So it's something that needs to be really fast, and we don't want to overload the network with bloat. since it's very small pieces of information, we want to keep the signature small as well. And elliptic curve really helps you there. And then the third one is GOST, which is a Russian system that's been standardized. And there are some legal requirements on the Russian side of things that they have to use these algorithms. So there is actually a standard for that as well. And so that is being used. Those are the three major ones.
So maybe it was on one of your final slides, you skipped one of them a bit quickly, but what happens if, like, you as a parent, when you update your key, do you then sign all your child's keys immediately, or how does that work, and how much time would?
Okay. If I, as a child, want, this gets complicated quickly, and now we're getting into the dragons. So I warned you about. we are now leaving the tourist safe area. So actually, every zone has two keys. One that it gets signed from above, from the parent, with the DS record that I mentioned. And the second one is used for signing all the records in your zone. And then your first key signs the second key. There are administrative reasons for this, because it turns into a nightmare if you have, what was it? There is a situation where the parent can suddenly get into a position of having to sign all the children's keys at once if you're not careful. So by splitting it into two keys, you can replace one at a time, and that turns the administration into something doable as opposed to something impossible. Anyhow, when you rotate a key, either of these, if you rotate your zone signing key, the lower key here, you can add a new key, and then you sign all your records with first the first one and then the second one, which will create, you have the normal address record and you have an RRSig record for that, but now you will have two RRSig records while you rotate. And then eventually you will take out the old key and sign again with only the remaining one key. Now, in every of these steps, when you add a key, you have to sign with your upper key all the keys that you have in operation further down. But that's a small thing because you do that with your equipment. So if you add a key down here, sign the key set, all the keys together, sign the zone with both keys. Eventually, sometime later, you remove the first keys, sign the key set, and then with the remaining key, you sign all the zones. All the records in your zone. If you replace your key signing key at the top, you add another one, and now you have to go to your parent and say, I have two keys. So you have two DS records that are signed by your parent. And then you sign both your keys with both your zone signing, your zone signing key with both your key signing keys. And then eventually you remove the old key, you talk to your parent, and you sign your zone signing key with your key signing key. So every rotation is a two-step thing, but by decoupling these, we don't have to sign the entire zone when we replace this key, and we don't have to have the parent do more work than necessary. But it's, interaction to the parent is the thing we want to avoid or automate. And that's why the CDS record has been invented.
Can we make this the last question? We're running a little bit late, so I'm just this is the last question. Afterwards, can you approach Liman directly?
Yes.
Because we'll take a short break, 10-15 minutes, and then you can ask Liman questions directly. But please go ahead.
A quick one then. You mentioned that you are running DNS and NTP. Have you considered also running trusted timestamping?
Yes, we do.
We do?
Time stamping. Yes, we have considered that. We do have a secure NTP service, so you can get signed time from us.
That's different.
But that's a different thing. So yes, we've been talking about that, but we are not there yet.